to do what I would like to do at least what I feel like is kind of an interesting discussion on how all this works today. And so let me start you off with this. Do you guys remember way back in algebra or perhaps a geometry class?
Oh, it's arc length.
Hello. Hey, check this out, guys. Let's see if you guys remember this. Do you guys remember in geometry class, or maybe it was in algebra class, or maybe it was both, at some point or another, wasn't there a question posed, something along the lines, what is the shortest distance between the blue point and the red point? Well, there was like lots of different ways this was presented, but it kind of boils down to two different ways that are really the same way. So in algebra, it was probably presented using what we call the distance formula. Yeah. And maybe it was derived for you, or perhaps even in geometry, you were shown how to do this using a different concept, but it's still the same concept. I don't think we need to do anything perpendicular, to be honest.
I mean, it's the hypotenuse of a right triangle.
There we go. And if we were trying to find the length of the hypotenuse of a right triangle, what would we use? No, not if we're talking about right triangles. How about the Pythagorean theorem? Yeah. Wouldn't we find the length of, so like if this was a length of 3, and this was a length of 4, couldn't we say 3 squared plus 4 squared equals, we'll call this distance squared. We do a little work when we figure out that 5 is the distance. That's right.
It's a 3, 4, 5.
It's a 3, 4, 5, just like a 6, 8, 10, right? Or a 30, 40, 50.
300, 400, 500.
Oh, that too?
Dude, 3,000,
Okay.
4,000, 5,000, those are my bread and butter.
Okay. I don't know if I can count that high, but it's good for you.
Thank you.
So, if you can understand that, I think you have a good chance of understanding where all this stuff that we're going to talk about today comes from. The end result for today is going to be kind of the question of, can you use these? But I did want to show you where these come from. So, instead of starting with something like that, what I want to do, I'll do this off to the side, and I'm going to say I've got a graph. And instead of this graph being what you're used to, man, I really hope you pay attention because I think this is pretty good. Instead of the graph being a straight line, what if the graph was curvy? Hey, Meg, Santi. This is worth your time, I think. I really do. Well, stop saying sorry and just listen. Okay. So, obviously, this is a little bit more complicated than figuring out how long a straight line is because this is not a triangle. It's no part of a triangle because it's obviously got some curve to it. However, we can kind of use that idea of the distance formula or the Pythagorean theorem to help us figure this out. So here's what I would say. What if I wanted to approximate the length of this curve? Couldn't I do something like this, where I maybe put a point right about there, and I connect that with a straight line segment, and then another one right there, and then this one would be pretty good because the purple graph almost looks straight there. Then there's that one, and then that one, and then I would connect to the end. So can you see how even what I've drawn there is not bad, at least at this scale, right? It's like a reasonable approximation. And if we could just use the distance formula, 1, 2, 3, 4, 5, 6 times. If I could use the distance formula 6 times and add up all those little lengths of those line segments, this would be an approximation, wouldn't it? And it would be reasonably okay, I guess. How could I make this better? Instead of just having a decent approximation, make it a great approximation?
Infinite.
Oh, you jumped right on past where I was going, but that's where we would eventually go, right? Well, wouldn't like 25 be better than 6? 25 little sub-segments, and then 1,000, and then Meg comes right over the top with what if we had a super huge, no, it's where we're going, so you shouldn't apologize. Okay, so here's what I want to do. I'm going to pick out one of these segments. Guys, man, I know you're excited about the distance formula. Try to contain it.
have no idea how exciting.
I'm going to pick out one of these little segments that's drawn at the angle that'll kind of help you visualize this. So I'm going to pick that second one right there. So if I've got that second one right there, wouldn't you all agree with me that this could be represented with a delta x on that side? I don't know why it's not showing up. It's showing up right here. And a delta y on that side. See, it's like nicely written.
And it's just not doing that.
I might have to shift gears out of technology. Please, I want to have a video for Jack. Come on, computer, you can do it. See it right there, Aiden? You see the delta x and the delta y?
Yes.
Y'all see the delta x and the delta y
Um,
that aren't up there yet? Do you see them? I don't know why something's frozen here.
I can see it in my mind and it's beautiful.
Bummer. Okay. Guys, hey, I know that anytime there's a technology glitch, it's time to just start gabbing, but please resist. Okay. Oh, it's starting. Can you see it? It's part of a delta. We'll just be patient, I guess. Okay. So this little triangle here, part of this curve, like so. Oh, okay, maybe it'll work now. I'll leave that up there just in case it doesn't work anymore. Would you be okay if I listed segment length 2 by saying that segment length 2 would be this long? D equals square root. Oh, it's going to be like that, huh? I'll leave it up here. I guess actually Jack has the best view right now because he can see my screen. He will be able to. Would you be okay with this? If this is delta x, this is delta y, and this is the segment length. We'll call that d for distance. There it is. Okay. We're getting there. You okay with that from a distance formula, Pythagorean theorem perspective? Okay. Well then, let's... So I'm sorry, say it one more time.
for the distance of the delta.
Oh, I wrote delta x twice, didn't I? It should be delta y.
Good catch.
We got what
I think I was saying it right, and looking up and seeing I got myself confused and wrote it wrong. Okay, that's good. So then, wouldn't you guys agree with me that in order to find, and I'm going to erase this part here in a second, hopefully it'll actually show up, wouldn't we need to go plus another, please don't write all this, wouldn't there need to be lots of them?
An infinite
Are there
accumulation.
6 of them or 1,000 of them? If we go with Meg's idea, we'd need like an infinite number of them. Maybe it's an infinite summation or infinite accumulation of things. We'll go there in a second. But let's just acknowledge that I'm going to need to add up a whole bunch of these in order for this to be
I'm a real gamer.
what I want it to be. So if we're going to be adding a bunch of stuff up, isn't that a sigma situation? Okay. So I'm going to say what I really want here for the full length of my curve would be sigma from I equals 1 to n, giving me the flexibility to have 6 subintervals or 1,000 or 1,000,000 or maybe even Meg's idea of something approaching infinity. So sigma from I equals 1 to n, and then in here I would just write delta x sub I squared plus delta y sub I squared. And that little sub I means, is it the first segment or the second or the third or the fourth or the fifth? And, so if I made my sigma I equals 1 to 6, that would fit the way that I drew my picture here because I've got 6 little sub-segments. But if I wanted 1,000, it would be I equals 1 to 1,000, so on and so forth, taking progressively more or less work as you added more to this. I'm going to do one little mathematical thing here to get the ball rolling in the right direction. In that radical, I could actually factor. What I could do is I could factor out a key factor, something that's pretty important, and that would be delta x sub I squared. So if I were to factor delta x out of both of those terms, what would be left over for the first term? 1, yeah. And then let's keep in mind that factoring is really just division. So if I divided a delta x out of each of those terms, what would that second term be? Delta y over what? Delta x? Yeah, it'd be delta y over delta x. So we go delta y over delta x, both of them squared.
Oh, you
Okay, so you're starting to see this take shape a little bit?
rascal.
Okay, so we really now at this point need to visit what Meg said, and that's if we want a perfect length of the curve, perfectly smooth representation, we don't need 6 segments or 1,000. We need infinitely many of them, right? Making them all essentially 1 point long. And the way we do that, of course, is with a limit. So I would say limit, actually I'm going to give myself a little more room. I'll come over here. So limit as n approaches infinity of that whole thing. So limit as n approaches infinity of sigma from I equals 1 to n. And I am going to do a little bit more arithmetic magic here. Inside here I'll have 1 plus delta y over delta x. But I'm going to say if you're squaring the top, the numerator, and you're squaring the denominator, isn't that the same as the whole fraction being squared?
Mm-hmm.
Like y squared over x squared is the same thing as y over x quantity squared. Okay, and then the square root of delta x I squared would just be delta xi, right? Because the square root would cancel right on out of there with a squared. So I took that outside the radical. And this is actually where we make the big leap. You can kind of see it already, can't you? Isn't this the definition? Isn't this a Riemann sum? This is the definition of an integral, of a definite integral. It's the limit of a summation as the number of little sub-intervals heads towards infinity. Therefore, the width of the sub-intervals is heading towards 0. So this right here would be integral from whatever the interval width is, from a to b is usually how we represent that. And then it would be the square root of 1 plus. Well, then we have a different way of writing this, right? If the number of little delta x's is heading towards infinity, instead of writing delta x, we usually write dx. Well, that makes the delta y's, the number of them at least, head towards infinity. We usually write that as a dy, right? Leibniz's notation of like infinitesimally small partitions. So this would now become dy over dx, quantity squared. And the same thing with that little delta xi on the outside. If the number of subintervals is heading towards infinity, it really is a delta x, but we usually write it differently because it is kind of special. So we write it as dx, and looky there. We've got it. But it's still kind of slow. It just showed up. There we go. So the whole point of that is not necessarily so that you can just memorize it and reproduce it. The whole idea is that when you see formulas like you see up there, you don't think, well, gee, my book said it or my teacher said it, therefore it must be true. Hopefully that is the case, but you can at least maybe have a sense of understanding where it came from.
Why can't you just take the derivative of the equation and just do the integral from a to b of that?
Oh.
Okay, so say that. So say it one more time. You said it really
Why can't
fast.
you just do take the derivative of like the equation, like the purple line?
Okay.
Have the equation to the derivative and do the integral from a to b of that.
Well, if I did a derivative, that
Or
would
just
give
do
me
like-
the slope.
Or just do a change in that. I don't.
Are you saying the area?
No, the area under the curve of the derivative isn't that the same? Isn't that what we're calculating?
No, we're not calculating the area of the curve. We're calculating the length of the line of the little curve.
But if you do the derivative of that and then do the area under the curve, isn't that the same thing?
If you do the derivative of what?
Of the purple line.
The derivative of the purple line, that would give you the slope of the purple
If
line.
you do the integral from a to b of that, isn't that the total distance traveled?
No, huh? So let's see here. So if I have f of x and I differentiate it and I get f prime of x, and you're saying do a definite integral. Okay, so then if I do an integral from a to b of f prime of x, by the fundamental theorem of calculus, this would give me f of b minus f of a. So this would give me the difference between the y-coordinate at b and the difference between the y-coordinate at b and a. Right, so this would be essentially like the displacement. It would be what is the net change in the y value from here to here. So what this would effectively, if we did that with this purple curve, I'll try to sketch this in. What that would effectively give me is my delta y. So Santi, it would give me, if we have this imaginary green dotted line, let's see here. There we go. This imaginary green dotted line, that would essentially tell me the distance between the two horizontal green dotted lines. How much did the y value change?
I was just thinking like in terms of like velocity and like position, if I were to then like.
So, okay, you bring up such a lovely point. So up till this point in time, when we talk about velocity and position and acceleration and speed and all that stuff, they always start off with an object is traveling along the x-axis or along the y-axis, blah, 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 find the total distance traveled, find the speed, whatever, right? So when you have a graph like this, it's moving in 2 dimensions. It's no longer moving in just a single dimension like the x-axis. It's moving left and right and up and down. So there will come a time in the very near future when we will have a particle not moving just along the x-axis, but also up and down and back and forth. And one of the questions you could be asked is, this object went from here and up and down, and it crossed over its path, and it went down here, came over here. How far did that thing go? And we're going to have to use something like this again. It's the 2-dimensionality of it. I think, Santi, I think your idea would be good if it was just moving up and down only, or left and right only.
Right.
But because it's 2-dimensional, it's not so good.
So this is definitely getting ahead of myself, especially with what you're talking about. But when we're doing when the particle's doing this, are we just gonna have to break that down into multiple different functions? Like, because obviously it's not a function for when it goes up and around because it's not 1-to-1 or whatever.
It's a great question. So what we're gonna find, and this will be true in this course and many future calculus courses that you have, is that it's going to be very often easier to define a function what we call parametrically, where x is a function of time and y is a function of time, but y may or may not be a function of x.
Oh, okay. Yep.
So we'll break it down into parametric components, which if you're doing physics, it's going to feel very physicsy because we're going to break it down into an x of t and a y of t.
Yeah.
And we'll break it down into horizontal and vertical components and deal with it from that perspective. And if you do take calculus 3 somewhere in the future, you'd have an x of t and a y of t and a z of t, or an I hat, j hat, k hat, maybe if you use stuff like that. And so then you'd have 3 dimensions, but we're going to certainly you'll use parametric a ton, especially like in a 3-dimension, like a 3-space calculus situation.
Okay.
So, yeah. Sure.
I just have a quick question. So we go from the summation of root x, not root x, delta x.
Like my
squared.
second to last step to my final step,
Yeah, where do you drop? You don't drop it. I just don't know where it goes.
where the
Delta xi, and then.
so the delta xi becomes dx. If the
'Cause you're
number,
gonna
so
have
it's just
enough-
a,
we're
it's
just
more of
gonna have
a,
like.
it's
an
more of a
infinitesimal.
naming thing than it is a technical thing. So so really, honestly, if we wanted to, we could, when we say wrote out some integral of whatever, if we wanted to write it out as integral from 3 to 7 of cosine x, instead of dx, honest to God, we could just write delta x.
Because that's just the.
And that's really what it is. It's just that when we say the limit as n goes towards infinity, those delta x's get super skinny. And so to honor that, essentially, we say, okay, we're going to call it a dx
Gotcha.
instead of a delta x.
I got you.
So, and one could argue that it's easier to just go with a d than a triangle. So it's a little bit easier to write, but it's just that whole limit as n goes towards infinity concept. We're signifying that. Great questions, you guys. So who knew you could find the length of a curve? Let's do it. So these formulas up here are things that hopefully after our discussion here for the last 20 minutes or so, hopefully, if somebody were to ask you about it, you could give like a pretty good answer to it. But really, we want to be just really utilitarian about it and just say, hey, do you know how to use this? Like, that's really what you're going to be assessed on. I'm not going to assess you on, hey, can you derive this for me, this derivation. I mean, if you can, that's awesome. I think that would probably help you remember it. But I want to just see if you can actually use it or not. So here's an example of a question, a really simple question you could be asked. It says, find the arc length of y equals x squared on 2, 3 using either x as the variable or y as the variable. And reading this, I would be remiss to not expand on what 2, 3 means. Let's call this 2 is less than or equal to x, which is less than or equal to 3. That's the typical interval has to do with a domain, but based on the way this question is worded, this could mean something different, right? Really could. So if you were doing something like this, you would remember or hastily derive one of the two, the way to find this, and we'd say that the arc length is equal to the integral from x equals 2 to x equals 3, and then it would be the square root of 1 plus dy dx squared dx. So, clearly dy dx is a pretty easy one on this one, so it'd be just a 2x in there. This would give me, of course, the integral from 2 to 3 of square root 1 plus 4x squared. There's all kinds of tempting and terrible things somebody could do here, like saying the square root of 1 is 1, and the square root of 4x squared is just 2x, and all those horrific crimes against math that could happen. If you're really honest about this, I don't know that there's going to be a real simple antiderivative. So maybe this would be a Math 9 situation, right? So maybe grab your calculator. Let's do a little Math 9.
Yes, sir.
Thank you.
Yes, sir.
Let's go that route.
Yes, sir, we do.
I'm trying to think here. I think this could be done with something called trig substitution using tan theta, I want to say. I could be off.
Oh, that sounds so fun.
It's not going to work by substitution. It's not going to work by parts. And that's kind of the end of our toolbox right there. Other than something called trig substitution, I think you could use tangent to do this one. Although, no, the square root really screws that. No, I don't even know. Would it be a secant? No, because secant has to have subtraction. I don't know. I have to do some thinking about how to do this without some kind of technology. Hey, what are you guys getting for an arc length?
5.1.
Let's go 3 decimals just for the...
5.1.
Oh, and then 2 zeros? Okay. So 5.100. Okay. So then this also suggests that we could use y as the variable, and presumably we would get the exact same answer no matter what variable we used, as long as we did it right. So this would be the integral from, no longer would it be from x equals 2 to x equals 3, but it would be from 4 to 9. That's right, because y equals x squared. Then the range would simply be from 2 squared to 3 squared. So from y equals 4 to y equals 9. It would still be the square root of something squared, but now it would have to be a little bit different, right? We can't plug an x in there. What would I need to do?
Solve for y and do the derivative.
Solve for x.
And do the derivative.
Yeah, so it'd be y to the 1/2, plus or minus technically. We know in the end it's not going to matter because we're just going to square it anyways. Yes, sir, Logan.
So you solve for x and put the kind of the y function in, or derivative of the y function in the formula. So why don't you do that with the bounds?
Do what with the bounds?
You solve for x and then.
So I'm trying to find what y is.
Yeah.
So I know that y relates to x with y equals x squared. So that tells me when x is 2, y is 4. We're literally taking this right off the graph. So this is part of a parabola. I'll erase this in a second. So the parabola is just our most generic parabola from 2 to 3. So the whole parabola, oh, that's one of my better parabolas. There we go. So the whole parabola looks like that. Let's say this is x equals, bless you, 2. And this is x equals 3 up there. So we're only talking about this part right here. This would be the point 2 comma 4. This would be the point 3 comma 9. So we're either going to accumulate from x equals 2 to x equals 3, or vertically from y equals 4 to y equals 9.
Okay, I guess I was just a little confused as to because you use one function, y equals x squared, to get your bounds, and then you
Same equation. I just solved for x. We could even, you know what would be cool? We could even do, well, no, that would be messy. Well, I was going to say we could do like kind of a backwards implicit differentiation, but it's easier just to solve for y. I don't think that makes a lot of sense.
Because then you
Or solve for x, I mean.
x equals square root of y for your as the other function. I was just a little confused as to why
Okay.
we're kind of using two different functions.
We're using the same thing though. Think about it. Like if I decided to use this one, and I said, hey, when x is 2, what's y? Wouldn't you say y to the 1/2 equals 2? And what would you do to get the y by itself?
I guess.
You square both sides, you get y equals 4.
Okay.
So it really is the same equation. It's just a different form of it, depending on if I want to be solved for y or solve for x.
Sweet.
Okay, so x prime then equals 1/2 y to the negative 1/2. So that goes in here. Let's see here. How does this turn out? This is a little more interesting looking. So this would be the integral from 4 to 9. This would be the square root of 1 plus 1/4 y to the negative 1, right? dy. So that's not going to turn out the way I was hoping. I thought we could do this without the use of a calculator. But anybody done it and got the same thing?
Yep.
Okay. So approximately 5.100 for the length of that parabola. So I think maybe the lesson we learned here is there are going to be certain situations when x is really easy to use. Other situations maybe y is better to use. Unless otherwise specified, you pick, right? You pick the one that works best for you, and it's probably going to be pretty obvious based on the way the question's presented.
Oh, that was kind of my question. How would you know?
I look at this one and I say,
Just because it's.
I look at the setup and I'm like, man, everything's already in terms of x,
Yeah, might
so
as
I'd
well
probably just use x.
Yeah.
But there could be some complicating circumstances where you're like, whoa, actually y would be better. And you go with that. Again, it really kind of depends on what's presented and the form that it's presented in. Say. All right, so we got our other example here today, example 2, and I'll flip over to that. You can do the same. So this one says you got this figure below, region R, and it's bounded by the trig graph and the line on the interval from, and again, I want to clarify and say that this 0 to 3 is, in terms of x, so it'd be 0 is less than or equal to x, which is less than or equal to 3. So the first part says, write an expression involving an integral that expresses the length of the boundary, bless you, of region R. So in other words, if region R was like a field, say again?
Looking for like the perimeter of the shape that's
Perimeter of it, yeah. So like I was going to say, if region R was like a field and the shapes were the fence, it would want to know how long is the fence, right? We would want to know how long is the fence all the way around there. That highlighted, oh, why is it so laggy? It's been so good for so long, and now it's lagging on us. There's a bottom of that, and it's not showing up. Okay, so write an expression for the length of the boundary of region R. I don't know, I'm looking at something. I'm wondering if there's some kind of a strange typo in here. Can you guys find real quick what point B is, the coordinates for point B? I guess. No, I guess that is 3 out there, isn't it? No, yeah. So it'd be cosine of x equals negative 0.5 1/2 Peyton, are you just giving up?
Oh, no, I'm great. Just looking at it sideways.
Okay.
The intersection is 2.094, comma, 953, sorry.
2.9094,
2.094,
comma,
2.953.
okay. Oh. Hey, guys, sorry, I just figured it out. Like the whole reference to 0, 3 is just saying like the picture shows that interval 0 to 3. It's not saying B is X equals 3. Because looking at it, like there's no way that B is, or X is 3 there. It's close. Sort of close. It's just saying that this is the picture that you're seeing here. Okay, so now that we got that point settled, let's take a few minutes, see if you guys can figure out the length of that boundary of R. Square root 1 plus 0.5 quantity squared dx. I think that's easier.
It was so easy.
I think it's easier doing it that way.
Row your own boat. It's
Oh, negative. I lost my negative in there. But it wouldn't matter anyways, would it?
Doesn't matter though.
But we want to try to do it right, so let's do it right. So right there. Oh, look at that. Negative 0.5 squared. There we go.
Shut up, you're the
Did y'all
only
get-
one who will vote the next election?
Did you get an answer for this?
Hey, no, he won't.
5.265. Any agreement?
You know what I'm talking about. And you.
Anybody else get this?
Senior.
Hey, Logan, did you get 5.508?
Yeah.
I got 5.265.
Ooh.
5.265 as well.
Guys, we have like 2 minutes to settle this.
Let's fight for it.
Alright, I'll put in my calculator.
Fight with your calculators, not your
My
fists.
calculator.
Maybe we can use our
Don't throw the
calculators instead
calculator.
of- oh, darn, you made
Fight by
one
pushing the
second.
buttons on the calculator, not with kicks and punches. I don't know what the answer is.
Wait, is one of us in degrees?
Oh, wait,
Oh.
physics class, and degree.
Oh, degree mode?
I blame physics.
Radian.
Yeah,
We do
I
want to
blame
be in
physics.
degree mode, or radian mode, because all these are in radians, not degrees. So 5.508 was right.
Radians, I would have gotten 5.5.
So there we go. For Jack's sake, Jack, I hope that you were in radian
Like a
mode.
rusting star.
There we go.
Hey, I'm still excited.
All right. Hey guys, so the plan is that on Wednesday, we'd review and make sure that we're good with solids of revolution and cross sections. And if you want to do some more practicing with this, you can. There is a section on surface area from revolution that we don't have to do. It's another one of those topics that we've done at times in the past that we are not going to be doing this year. So anyways, that would be it.
Thank you.
You guys are out 31 seconds early. Have a great day.
31 seconds.
Yes, enjoy all of it.
That'll help me. You avoid traffic.